Okay guys, so first time I'm showing on play. Okay, so we are going to look at the proof of the Cauchy-Riemann equation. Now it states that we all know, because it's too long I can't start stating the proof. So let's start with the proof. Now the first thing we are going to do is to look at the definition of we all know what we did in calculus 1, like the definition of differentiation, which states the limit as h approaches 0 we all know this definition. Yes, we all know this. So it is with our knowledge on calculus 1, we are going to approach this. That's what we are going to use to approach this question or this particular proof. Now let's assume this is what we do when we are dealing with real function. Now how we approach it when we are dealing with complex function is a little bit different. Now the first thing to do here is to assume this. We are looking for the derivative of a complex function. Anyway, and this is surely going to be equal to, as the change in z approaches 0, of f of what? Z plus what? dz minus f of z over dz. Yes, we are good to go. Now we all know by definition f of z is this: a function, a multivariable function containing a real part and what? An imaginary part. So same thing we are going to do here. So this is surely going to be equal to, I hope it's showing. So we just have to rewrite this ugly boy here using this. So it's just going to be u x plus dx comma y plus dy plus iv x plus dx y plus dy minus u of xy minus I of what? xy. Now this is this part here over change in x plus I change in y. What we did was just to represent z back in terms of x and y. Very straightforward, nothing too hard or serious. So now we can all see that this particular notation does not match any particular. This is actually absurd. Like, this statement is actually wrong. Why? Because there is the z here and we don't have any dz here. That simply means, because if we look at what we have been doing since, dz is actually equal to dx plus I dy. So same thing is going to apply to this. If dz approaches 0, dx is also going to approach 0 and dy is going to approach 0. So I'm just going to write this as dx approach 0 and dy approaching 0. Now the next thing to do is to break this particular limit into two parts, which is the dx part and what? The dy part. Then we'll be able to decompose the question and finish it off. Give me a few minutes to clean the board. Okay, so this is where we stopped in the last part. So I cleaned the board and let's continue. Okay, so since I told you we are going to break the question into two parts, so this is the first part, is the dx part. Now the first thing to do here is just to take all the u's to one side and take all the v's to one side, or simply say take the real parts to one side and take the imaginary parts to one side. Then it's going to look like this. Minus ux plus minus v of xy over change in x. Now looking at this, by definition, this is just simply the definition of a derivative, but just that it is multivariable here. So simply this is just the partial derivative of u in respect to x, and this partial derivative of v in respect to x also. So for this part, like when we took the limit of the whole complex function in respect to x, we got this. Plus I v xy in respect to x. This is what we got. So when we do for dy, anything we get, since they are equal, we equate them together and compare both sides, and we are done. So for the dy part, we are going to have ux plus dx, y plus dy, minus ux of y over change in y minus the limit as dy approaches 0, v of x plus dx, y plus dy, v of xy over change in because you can see it here. So now for this, looking at this, because of these imaginary constants we have here, we have to multiply the numerator and the denominator by the conjugate of the imaginary constants. Obviously this is just going to be minus I times all this. Are we together? Or we can simply say I times all this. It's still same. Now for this one, we are just going to have when you multiply the numerator by I, you should have I times I. That will give us minus 1. When you multiply I with the denominator, you also get minus 1. So you should get plus 1 in general. So when I multiply, so that I should have something like I times the partial derivative of u in respect to y. Are we together? And for this, I should have minus the partial derivative of v xy in respect to y. Simple. Are we together? So we are just going to merge this part and this part, this part and this part, and we are done. Okay, so let's begin. So eventually when I merge them together, so okay guys, sorry, there was an error. You know, when we are multiplying the numerator and denominator by a complex constant, I times 1 is just I times I is minus 1, so there I will get minus I. So when we do same thing here, I times I is just minus 1, I times I is also minus 1, so minus 1 divided by minus 1, you get plus 1. So eventually from this we got the negative I times this plus this. You can pause it now. Okay, so when we gathered the result of what we got from here and here that other time, I told you they are the same. So surely they are going to be equal to each other. Now the next thing we do here is just to compare both sides. Like surely if they are equal, therefore the real part here should be equal to the real part here, and the imaginary part here should surely be equal to the imaginary part here. So this implies you should have this should be equal to this. Surely. And dv over dx will be equal to over dy. You can simply write the equation. Therefore, this is just the proof. Therefore, we have this as we all know the Cauchy Riemann equation. That's all. And so this is just the Cauchy-Riemann equation. That's the proof for it. So thank you guys. We'll see in our next class. Peace.